So, by the way, that's just two strain measures we chose, right? The one, just like I said when we talked about one-dimensional strain, you have engineering strain, logarithmic strain. It really just depends on what you choose to reference it to, and you could reference it to that wall over there if you want, right? Well, so the two strain measures we just defined, the Lagrangian and the Eulerian, they reference the deformed and current configurations, but there's nothing to say that we couldn't choose some intermediate configuration or the wall over there to reference to, okay? So we can go on defining, so I guess another, maybe ask a question is, how many valid strain measures are there? Just two? I mean, that's all we talked about. How many are there? There's an infinite number because how we choose to reference it is arbitrary. Okay? Now, I would argue that they should all collapse to the linear strain in that limit. Right? In the limit of small displacements, they should all collapse to the linear strain measure. And the reason for that is because there's a geometric interpretation of the linear strain. And this geometric interpretation of the linear strain is actually where that factor of 2 came from. If you remember, we just sort of arbitrarily said that this is 2e. But I didn't really say where that 2 came from. I just said we'll make it clear later. Okay, so now is later. We'll look at the linear strain or the geometric interpretation of the linear strain. Okay, small strain. So we're going to start with a little cube that has width dx1, height dx2. And this point here we'll label A, and this point here we'll label B. Okay? And I'm going to greatly exaggerate the strains, but we're going to strain that cube and displace it, deform it, right? So I'll kind of superimpose the original cube here. And this point A prime, and this point is B prime. Okay. This distance here we're going to say is U1. This distance here is U2. This distance here is the change in U1 with respect to x1 dx1. And this distance here is the change in U2 with respect to x1 dx1. All right? And then we're just going to sort of write down our linear or, sort of undergraduate definition of strain in the x1 direction. So the strain in the x1 direction is equal to A prime B prime minus AB. And so the length of the line segment A prime B prime minus the length of the line segment AB over the length of the line segment AB. So it's sort of an engineering strain. You're going to divide or normalize by the original length. And of course, the original length is just dx. AB is just dx. So we have A prime B prime minus dx1 dx1 is equal to A prime B prime over dx1 minus 1. So the line segment A prime B prime is equal to, right, this the square root of the sum of the squares of the components, right? So in the x direction, the component is like dx plus du1 dx1 dx1. We square that, and then in the x2 direction, we have du2 dx1 dx1, and we square that, right? And then we take the square root of this whole thing, okay? But I don't like square roots, so I'm going to square both sides of the equation. So when I square both sides, then I can get rid of this square root sign. And so then we're going to go back to we had this equation, dx1 equals to ab prime dx1 plus 1. And I want to square both sides of this equation. And when I do that, I'll have terms that have a prime, b prime squared in it that then I'll plug this guy into. And ultimately, when you work everything out, you'll have something that's like x1 squared plus 2 x1 plus 1 equals to 1 plus 2 du1 . All right, and then we're just going to ignore all the higher order terms. And so then we have this, just sort of this equation left. The 1's cancel, the 2's cancel. And what you're left with is that the strain in the x1 direction is equal to partial u1 partial x1. And, you know, if I went on and made these same geometric arguments for all the other strain components, the shear strains and everything, then, you know, what you'd see eventually is that the small strain is equal to 1/2 ui xj plus uj. So if you work through all the other details, you'd get that. So, you know, just to be clear, like, so in the 1-1 direction, if I substitute in I equals 1, j equals 1, then I get, right, then I get 1/2 is 2 u1 x1, right? The 1/2 and the 2 cancel, and I have u1 x1, which is what we derived sort of geometrically there. And so that's where the 1/2 comes from, because it shows up in the geometric argument for the small strain, okay? And so then when we define our large strains, we want them to be consistent in the small strain limit, right? And so that's why we said that they equal 2e.